Alright, we're going to continue our discussion on curve sketching. And we're going to move right into example 2 in this video. We're going to look at the function f of x equals x squared plus 1 over x squared minus 9. So from this, we can straight away find some asymptotes. So first, to find our vertical asymptotes, we need to find out what values set our denominator equal to 0. So if we take x squared minus 9 and set that equal to 0, what x values make that happen? Well, there's two ways you can do it. You can factor this, it's a difference of squares, or you can add 9 and take the square root. Either way, you get the same answer. You're going to get x is 3 and negative 3. So we've got vertical asymptotes at x equals 3 and at x equals negative 3. Those are also discontinuities in the graph. Now to find a horizontal asymptote, remember we can look at the leading coefficients. Well, first we look at the degrees, and if the degree of our numerator is bigger than the degree of our denominator, which is not the case in here, but then our horizontal asymptote would be x equals 0. Because the degrees here are the same, they're both x squared, we take the ratio of their leading coefficients. So we're going to have y equals, the leading coefficient of both of them is 1, and 1 over 1 is 1. So our horizontal asymptote, y equals 1. Now, our domain is limited this time. Because we know there's discontinuities, we've got asymptotes at 3 and negative 3, our domain goes from negative infinity to 3. It goes from, correction, not to 3, to negative 3. It goes from negative 3 to 3. Now we're not including negative 3. And then it also goes from 3 to infinity. And again, we're not including 3. Our range, again, because there's a horizontal asymptote here, our range is limited as well. Our range has two intervals. It's from negative infinity to 1 and from 1 to infinity. But we do not include 1 in the range. So now, let's find our first derivative. We need that to find our critical points. So using the quotient rule, we can write our derivative as x squared minus 9 times 2x minus x squared plus 1 times 2x over x squared minus 9 squared. And we're going to start with that. Now I do notice in the numerator both terms have 2x, so I'm going to factor that out. I have 2x times x squared minus 9 minus x squared minus 1. And I got that because I distributed this minus sign to the x squared plus 1. And that's all over x squared minus 9 squared. Now when I'm cleaning up my numerator, my x terms are going to actually cancel each other out. And negative 9 minus 1 is negative 10. If I multiply that by 2x, I'm going to get negative 20x over x squared minus 9 squared. So remember, our critical numbers we find when we set the numerator equal to 0, because that's the only way this function can ever equal 0. So if we have negative 20x and we set that to 0, the only way that's going to happen is if x is equal to 0. So we've got a critical number at 0. We're also going to test critical numbers at our discontinuities, which are at x equals 3 and negative 3 at those asymptote points. Because stuff still happens before and after those, it just nothing happens at 3 or at negative 3. So let's write our test intervals and find points for those to test out. So we know our intervals we're going to be looking at are from negative infinity to negative 3, from negative 3 to 0, 0 to 3, and 3 to infinity. Those are our intervals. We need to determine, are they increasing, decreasing, some concavity there, any maxes and mins, do we have any points of inflections, are still things we need to do. Now, for testing, I would take x equal negative 4, I would take x equal negative 1, x equal 1, and x equal 4. We're going to plug those into our first derivative to decide, is it increasing or decreasing? So if we put negative 4 into that first derivative, we're going to get 80 over 16 minus 9 is 7, and 7 squared is 49. So we're getting a positive over a positive, which means this is going to be a positive number. I don't really care what number it is. I just know that it's greater than 0, which means on that interval we're increasing. If I put negative 1 in, I have negative 20 over, not negative 20, I'd have 20 over, let's see, we've got negative 1 squared is 1 minus 9 is negative 8, but if we square that, that's positive, and a positive make a positive. So if we put negative 1 in, then it's greater than 0, it's increasing. And that's okay that we've got an increasing and then an increasing. We know there's an asymptote between them. So something messes things up. And that's fine. If we put 1 in, we get negative 20 over a positive number. So positive and a negative make a negative. So f prime of 1 is less than 0. We're decreasing there. And the same thing, if we plugged 4 in to the derivative, we're going to get something that is also less than 0. Something that's negative. So we're decreasing again. And this is okay that this is happening. We do know, though, between the intervals negative 3, 0, 0, 3, we go from increasing to decreasing. So there is something happening there. In fact, because it's going increasing to decreasing, we know it's going to be a maximum happening at that point. So now let's find the second derivative so we can test for concavity. And I've run out of room on this screen, so I'm going to make a new one. If we want to find the second derivative, we're going to again use the quotient rule. So we can write this derivative as negative 20 times x squared minus 9 squared minus, or really in this case plus, 20x times 2 times x squared minus 9 times 2x over x squared minus 9 squared. Now let's clean this up. I do notice in both terms they've got an x squared minus 9 and a 20. So I'm going to factor that out right away. So we're going to bring out 20 and an x squared minus 9, which means in that first part we've got a negative x squared plus 9 plus we've got x times 2 times 2x, so that's going to give us 4x squared, and that's all still over x squared minus 9 squared. Not squared, I made one mistake. That shouldn't be squared, that should be to the 4th. Let me fix that in this line and the previous, because I forgot to square my squared. Okay, so now let's clean up what we've got. We can eliminate 1 x squared minus 9 on the top and in the denominator. Make that now to the 3rd. So we've got 20 times, when we combine those x squareds, we get 3x squared plus 9 over x squared minus 9 cubed. Now we can leave it like that, that's fine, but we can also factor a 3 out from the top, the 3x squared plus 9. Make this 60 times x squared plus 3 over x squared minus 9 cubed. It's not a big deal. We don't have to do the factor of the 3 out, but we do want to set the numerator equal to 0 to see if we have any inflection points. So if we go 60 times x squared plus 3 and set that equal to 0, we're only going to get an imaginary number from this, so we don't have an inflection point. So no points of inflection. Because we can't set that equal to 0. But we are going to still test for concavity. So let's take those critical numbers we used from that first derivative test. The discontinuities, excuse me, and set up some test intervals for this. So we can look for concavity from negative infinity to negative 3. We can look at it from negative 3 to 3 and from 3 to infinity. Now, if I'm trying to pick a number, I'd do negative 4, I would do 0, and I would do 4. Now we're going to plug these into, we're going to put them into the second derivative to determine are they concave up or concave down. And remember, we really are just worrying about are we going to get a positive or a negative number from plugging them in. So if I took f double prime, the second derivative at negative 4, the question is, if I put that in for x into 60 times x squared plus 3 over x squared minus 9 cubed, well, negative 4 squared is 16. 16 plus 3, 19 times 60 is a real big positive number. 16 minus 9 is 7. If we cube 7, it's a positive, so that means this is greater than 0, so we are concave up in this case. Now if I put 0 in, 0 plus 3 is 3 times 60, 180. 0 minus 9 is negative 9. If I cube negative 9, that's a negative number. A positive and a negative through division make a negative, so the second derivative at 0 is going to be less than 0. It's negative. So here we're concave down. And then if I put 4 in, well, 4 squared is the same as negative 4 squared. So that means this is going to be bigger than 0. It's going to be the same thing as if I put negative 4 in. So this is going to be concave up. Okay, so I'm going to open up another page and write down everything we know before I actually sketch the graph. And there's one other thing we do need to find, and that's the max or min value. In fact, we know it's a maximum value. Alright, so on this left side, I'm going to write everything we know. We know that we have a horizontal asymptote at y equals 1. We've got vertical asymptotes at x equals 3 and x equals negative 3. Those are important things to take note of. We know that we are increasing from negative infinity to negative 3, and from negative 3 to 0, we are decreasing from 0 to 3, and from 3 to infinity. We know we are concave up from negative infinity to negative 3, and from 3 to infinity. We are concave down from negative 3 to 3. The only thing I haven't found is if we have well, we know it's a max. We know at 0 we have a max. Just what's the y value there? So if we were to plug 0 into our original function, we would get 0 plus 1 over 0 minus 9. So y, or f of x, is going to return negative 1/9. Okay, now let's get sketching. So we've got our graph. We know we have a vertical asymptote at negative 3. We know we have another vertical asymptote at x equals 3. We know we have a horizontal asymptote at y equals 1. We know we have a critical number, a maximum at 0, negative 1/9. Now the easy part is graphing this middle part, because we know from negative 3 to 0 we are increasing, and we know from 0 to 3 we're decreasing, and then we know from negative 3 to 3 we're concave down, we're opening downwards, that's right, and then we're increasing from negative infinity to negative 3, being concave up, as well as concave up but decreasing from 3 to infinity. We've got everything we need here. We're done with example 2. We'll see our next examples in our next video.